Now we are going to discuss the main topic of this lecture, the four-way handshake. So in this segment we are going to talk about a few key ingredients among many of them that occurs when we first type in our Wi-Fi password and click connect. The same concept is broken down and used to perform an attack to get the WPA2 password as well. So understanding this part is pretty important. We will go from message 1 to 4 on the following pages respectively. So considering that both of those devices had their associations done, which means they both agree that they should connect to each other and they should start the handshake process. So before even sending message 1 of 4, which is the announce from router to the supplicant, what both of those devices has in common? The client is trying to connect to the Wi-Fi router, so that means the client knows the SSID of the router. The router also knows its own SSID, of course, and they both has their Wi-Fi passwords, right? So what they do have in common to make something from this? They have their Wi-Fi password and they know their SSIDs. So we can use these two values to generate a pairwise master key. How it is generated, I already explained that in previous video. So they can now generate the pairwise master key. So after their pairwise master keys have been generated, by the way, let me just clear out something. There is never a password transaction that happens at all. Like the pairwise master keys or the pairwise transient keys, which will be generated in later, they are never actually sent in through the air. It's not that when a hacker sits in the middle and it just grabs all the information that they are sending to each other, and within the informations there is a password lying somewhere in the middle, and the hacker is just brute forcing the password like I just showed you, and he could find out the password. Well, that is not what happens. Many of my friends who are currently studying penetration testing, they also do not know this, that the password is not exactly sent over through the air. So anyways, now they both have their own pairwise master keys. Now the Wi-Fi router or the Wi-Fi authenticator sends a nonce message. So what is a nonce? If we consider it on this word, nonce is basically a number that is used only once, because this nonce value will never be used again. Alright, so A means authenticator, so basically authenticator nonce. A random number is sent from the router to the supplicant, right? On the second message, when in the first message the supplicant gets the A nonce, it generates its own nonce, which is called the supplicant nonce or S nonce. It sends it to the Wi-Fi router. In the second message also an MIC is sent, but we are not going to concentrate on that now, but in a few minutes. So if we just remove the MIC from here, what the router and the supplicant has in common, they both have the A nonces and S nonces, because the router knows its own A nonce, and on the second message it just got the S nonce from the client, and from the client side it generated its own S nonce and it got the A nonce in the first message from the router. They all know their MAC addresses, right? So what can be generated in this section? Well, if we go to this part, they both have their pairwise master keys, they both have their S nonces and A nonces, and they both know their MAC addresses, right? So from this part they can generate something called the pairwise transient key, right? So the PTK is now generated for the both of the devices. Now the problem is, how can the supplicant and the authenticator exactly know if they has the same passwords? Because if this one is the hacker can give any password, right? And try to connect to the Wi-Fi router. It doesn't work, but they can, right? So then how the router knows that it's an invalid password? It's not that they are sending the pairwise transient keys to each other, right? Then how does it know? It's because of the MIC. Now, how the MIC is generated? You already know that the key used in MIC is the KCK or the key confirmation key. So where the key confirmation key is generated from? The key confirmation key is basically the first 16 bytes of the pairwise transient key. So if we go to this example, KCK, which is the key confirmation key, which is the first 16 bytes of the resulting hash from the PTK, right? So that 16 bytes is used as the key, and the payload you already know, which is the second message header info and the message itself, is used to compute the message integrity code, right? So now that message integrity code is sent to the router from the client, because they both has generated their own PTKs, right? But before the router generated its own PTK, the supplicant did that before, right? Because the supplicant got the anons and snons before the router got. So the supplicant generated its own PTK, broken that PTK apart, and the first 16 bytes is used to generate a mic, and that mic is sent to the router. Now the router got anons and snons, it can generate its own pairwise transient key, right? Now when the pairwise transient keys is then broken down on the router side, and the first 16 bytes are used to compute a message integrity code, also the supplicant sent its own message integrity code, and if those message integrity codes that the supplicant and the router has matches, then the router can know that the supplicant has the right password, which means the right pairwise master keys, the right pairwise transient keys. Now what happens when the router assures itself that the supplicant has the right key? It sends a message to the supplicant that you may now install the keys. Now I am not just explaining the complete process here. There is something called a group temporal key which is generated here, but it's not very important for this example or this tutorial, so I'm just avoiding that. So anyways, in simple terms, router says to the supplicant, we have the same keys, you can install the keys which are going to be used for the encryption process. And when the router says install the keys, the supplicant says, okay, now I am ready to actually transfer data by sending an acknowledgement to the router. So this is the simplest version of a four-way handshake that happens. So again, if I recap the whole thing, the router sends a random value to the supplicant takes the random value, generates its own pairwise transient key, and breaks the pairwise transient key and use some of it to generate a message integrity code, and then send both the message integrity code and the random value that the supplicant generated itself to the router. The router gets the snons value, it generates its own PTK and as well as MIC, and if those MICs match, then the router says, okay, you are ordered now to install the keys. And when the supplicant gets the order for installation of the keys, the supplicant sends an acknowledgement to the router saying, okay, I have installed the keys, now we are ready to make actual data transfers. That concludes the four-way handshake process. This is the process that is exactly used when we are connecting to a Wi-Fi router. This is the part where I explained how a connection between a supplicant and an authenticator actually works, but not exactly how the hacking works. So let's come to that part. When we are hacking the four-way handshake, what we do is we get all of the four messages from the handshake. So what now the hacker has? The hacker has the anons, the hacker has the snons and mic. Now this mic is the most important thing that is used here. So what the hacker can do, like I have shown you in the previous practical video, what the hacker can do, it can generate a pairwise master key for each of the entries in his own word list, right? So each of the pairwise master keys are then used along with both of the MAC addresses and anons and snons to generate a pairwise transient key, right? The hacker can also generate the pairwise transient key because the hacker also has both of the devices' MAC addresses and both of the devices' nonce values, right? Now the pairwise transient key, the hacker can break apart the pairwise transient key and use the first 16 bytes of the pairwise transient key to generate a message integrity code, and in every iteration of the brute force, the hacker simply checks if the resulting MIC matches with the stolen MIC from the four-way handshake. The process goes on and on and on until both of the MIC match. When the MICs match, then the hacker knows that the pairwise transient key is correct for both the supplicant, the authenticator and the hacker, and so is the pairwise master key, which means the hacker now knows what was the exact password that was used during the authentication, which was never shared in the air. So now we can see how we can hack the password of a WPA2 by never knowing the key at all, because the authenticator and the supplicant never shared their password or the important keys in the air. They just send authentications. So we can use those authentication messages to check our version of authentication to crack the Wi-Fi password. So after this video, I am going to show you practically with Wireshark how we gathered all the four-way handshake messages and how we can actually go ahead and hack the passwords out. So see you on the next video.